Hello everyone, welcome to the Microeconomic Theory class session on for the 9th of April. So I will today discuss couple of applications, examples of the extensive form game where we'll apply the SPNE equilibrium concept and sort of we'll see how this can be applied in variety of settings. So today's class will be short, so let's talk about the first example. Remember we were talking about this extensive of games where an individual can offer with 100 rupees can offer to share with another person who can say yes or no. So we'll see a version of an extended version of that game today. So think about two players now, each of whom have 100 rupees in their pockets, okay, and they are each trying to share a part of their 100 rupee endowment with a third player. So there are three players in total. So there are players 1 and 2, each of whom have 100 rupees, and they are each trying to share that 100 rupee with the third player, but the third player can accept the offer from only one of the players. Okay, so that sort of is the broad context. So we will consider two sequence of events and we'll see how the game sort of changes in response to the sequence. So here is the first sequence. So suppose player 1 first offers 100 rupees, a share of the 100 rupees. So player 1 moves first and offers P1. So here P1 is the share that player 1 keeps for himself, okay? And it is the player 3 who's saying yes or no. So if player 3 says yes, the game ends right there. Player 1 gets to keep 100. There is a player 2 who doesn't come into the picture so far. So he gets 0. The third player, since he has offered the deal, he gets the rest of the money, 100 minus P1. Okay, so that's the payoff if player 3 says yes to this offer of player 1. If player 3 says no, then player 2 comes into the picture. Then player 2 gets to make his offer to player 3. So this is player 2 who offers P2. Again, P2 is the money that he says he's going to keep for himself. Okay. And again, player 3 gets another chance to say yes or no. If player 3 says yes, since player 1's offer has been rejected, player 1 gets 0. Player 2 gets to keep his part of the offer and player 3 keeps the rest. In case second player's offer is also rejected, then everybody gets 0, okay, and the game ends. So this is one way this sort of sharing deal can go down, okay. This is a case where everybody sort of knows about their exact location, so we can apply backward induction, right? So we can start with player 3's move here. So clearly player 3 will accept any deal, right, at this point. So as long as P2 is greater than or equal to 0, we can say that player 3 will as long as P2 is less than or equal to 100, so which means as long as the payoff of player 3 is greater than or equal to 0, then player 3 will accept. So we write that 3 accepts if 100 minus P2 is greater than or equal to 0, or P2 is less than or equal to 100. Okay. So that's sort of 3 strategy in this node. Knowing this, P2, of course, what would P2 be? 2 keeps everything for himself. So knowing that, 2 chooses P2 equals 100. Okay, so that's sort of 2 strategies to keep everything for himself. Okay, now what would be player 3 strategy here, knowing that 2 is going to choose an offer 100? So now here player 3 will compare this payoff with this payoff. Okay, no, but this payoff is 0, correct? This payoff is 0, right, because of 2's optimal strategy. Now, so again player 3 will compare 100 minus p1 with 0. So as long as 100 minus p1 is greater than equal to 0, player 3 will accept, otherwise it will reject the offer. So again you see that knowing that player 1 will offer that he's going to keep everything for himself, p1 will again be 100, right? Because as long as p1 is for every p1 which is strictly less than 100, 3 strictly prefers to accept the deal because he gets strictly positive payoff as opposed to saying no, in which case he'll get 0. So when p1 equals 100, then his player 3 is indifferent between saying yes or saying no, because in both cases player 3 gets 0. So we can say that yes is a best response in that case. So player 1 also, so we say that player 1 also chooses p1 equals 100. Okay, so you see in this sequence of games 3 loses out, even though there are 2 players who are trying to share their part with player 3. 3 doesn't gain from this extended version, from multiplicity of people who are trying to share the money. Okay, he still gets 0, which is similar to the previous case where there was only 1 player who was trying to share his 100 rupees. Okay, so that sort of is the first part of the game. Now let's try to change the sequence of the game and make it a bit different. Okay, so now suppose player 1 and 2, they simultaneously choose so sorry, so suppose now 1 and 2 simultaneously choose p1 and p2. Okay, and then player 3 decides whether to accept one's offer or choose or reject all offers. Okay, so that's the so now I'm making 1 and 2's offer simultaneous. So previously 1 and 2 offered sequentially, and after each offer player 3 could say yes or no. Okay, now player 3 decides simultaneously, so both 1 and 2 makes their offer, and player 3 makes a decision whether to accept 1's deal or 2's deal or reject both. Okay, so let me write down the extensive form expression. So 1 offers p1. Now because it is simultaneous, I'm gonna do a dotted line here. So dotted line here means that here player 2 makes an offer without knowing what player 1 is offering. So 2 makes a similar offer p2. Okay, simultaneously with player 1, and then player 3 can see everything, all the offers, and then say yes to player 1, or says yes to player 2, or says no to everybody. Okay, so that's rejecting. N means rejecting all offers. Y1 means accepting only one's offer and rejecting two's, and Y2 means the other way. So now if player 3 accepts player 1's offer, then player 1 gets P1, 2's offer gets rejected, so 2 gets 0, and 3 keeps 100 minus P1. If player 3 accepts 2's offer, then 1 gets 0, 2 gets to keep P2, and 3 gets 100 minus P2. And here everybody gets 0. Okay. Now, knowing this, so now again let's try to see what will happen in the terminal node. Okay, in the terminal node, of course, player 3 is going to choose whichever action that gives him higher payoff. Okay, so if P1 is less than P2, then 100 minus P1 is bigger than 100 minus P2, right? So Y3 will accept Y1. So we say that 3 accepts Y1 if 100 minus P1 is bigger than equal to 100 minus P2, which is the same thing as saying P1 is less than equal to P2. Okay. Now notice that so basically this means that 3 accepts the offer of the person who says is going to keep less amount of money. Okay. Now what will happen in the first part? In the first part, the players are moving simultaneously. So suppose both P1 and P2 are less than 100. Okay, suppose it is the case. Can that be a Nash equilibrium? Now we are looking for SPNE. SPNE, we have already found out what is the optimal strategy for player 3 on the final node. So now for the whole game to be a Nash equilibrium, we want P1 and P2 to be best responses to each other given 3 strategy. Okay, because we have already ensured 3 strategies optimal.